Okay, I'm recording this video to just explain the solution to homework number 1. I won't be doing this for every homework set, but I thought it'd be a nice start on the statics. And so we've got 3 statics problems to look at. We have this interesting bent bar system that's moving on a slider. We have a known force here, and we have a rope force here, which places the whole system in equilibrium. There will be some reactions at point A, both force reactions and moment reactions, and what we want to do is find those force and moment reactions and find the tension in this rope. Now, one of the things we do notice is that the slider is presumed to be frictionless, and that's going to give us some hope for finding the rope force, and we're going to take advantage of that. We're also going to set up the rope force as being a force aligned with the rope, which means we will have a force that is acting in the same direction as the unit vector that the rope is pointing in. And so we need to find that unit vector. And so we're going to say that a vector that goes from B to point C will be the coordinates of C minus the coordinates of B. The coordinates of C being, I've got a 0, 8, 6, and point C is 0 in the X, 8 in the Y, and 6 in the Z. And the coordinates to point B would be 12 in the X and 4 in the Y and 0 in the Z. So subtracting those two vectors, we get a minus 12, 4, and 6. And calculating the magnitude of that position vector, Pythagorizing 12, 4, and 6, we get a 14. And then taking our 12, 4, 6 vector, dividing each term by the 14 will give us a unit vector in the RCB direction. So we can say that our force from B, or the rope force, is equal to the magnitude of the rope force that we don't know, times the minus 12 over 14, which is minus 6 over 7, etc. Now, the equation we'll solve to find the rope force, realizing there will be no reaction here at the point A because of the slider, will have no force in the Z direction, and so sum of forces in the Z direction that are shown equal to 0 because there's no unknown force here. And the force in the Z direction would be a positive 3/7 times FB, and then from the FD we would have a negative 75. Those two forces are the only forces in the Z direction. Sum them to 0, and we get that our reaction, or our force at point B, which is the rope force, is 175, and that's the magnitude. I said FBZ, no. FB is the magnitude of the rope force, and that is 175. Now, to determine the reactions at point A, we do two things. We sum all forces in the problem, including unknown forces at A, and we solve for the unknown forces at A. We solve for all moments about point A, including the unknown moments at point A, and get the reaction moments at point A. So to get the reactions at point A, we're going to sum forces equal at 0, or sum forces equal to 0. Then we're going to have the reactions that occur at point A in the X, Y, and Z, plus the force at C, or B, it doesn't matter, the rope force, plus the force at D. The sum of those 3 forces equal to 0. This is the unknown, and we'll solve for it. So our force at C is the 175 times the unit vector, and the forces given in the problem statement for the forces at D, and we sum those and solve for the unknown RA, and we get that the unknown RA is 130 in the X, minus 10 in the Y, and 0 in the Z we expected. If we didn't get a 0 there, we would know that we did something wrong earlier. Okay, and finally, to sum moments about point A, to get the unknown moments back here at point A, we're going to need to do some R cross F, and the R cross F that we're going to do is I'm going to do the radius from A to C. I'm going to sum moments about A. So I'm going to do the radius from A to C crossed with the rope vector. I could have done the radius from A to B crossed with the rope vector, and I promise you would get the same thing. If you're unsure of that, just go check it. That RAC crossed the rope vector is the same as RAB crossed with the rope vector. I could have picked a middle point somewhere along the rope and done just as well. Okay, but I also need RAD, RFD with respect to A, crossed with the force at D. And so going to C from A, I've done that before, that's a 0.86. Going to D from A is a 12.00. I head straight down the x-axis, and that's all. And I've got my rope force, and I've got my force at D. And so I'm going to write the equation that says, let's see. Actually, I guess maybe you weren't able to see these earlier. This was probably off the screen. I'll get better at this. Okay, so my R of C with respect to A here, R of D with respect to A, head right down the z-axis. Here is my rope force as solved for earlier. Here is my force at D, simply copied down. I'm going to sum moments about A and set it equal to 0, but I'm going to say that there is an unknown reaction set of moments at A to be solved for, plus the moment caused by the rope, plus the moment caused by the force D. And so again, my unknown moments plus R cross F plus R cross F, set all of that equal to 0. Here are the two R cross F pieces, intermediate answers that you can check. Here is the final R cross F piece of those two vectors, so those vectors added together. And I simply bring these to the other side to solve for the moments at A. And so the moments at A are a minus 300, a 0, and a minus 720. I didn't anticipate that moment about the z-axis being 0. About the y-axis being 0, but there it is. That's the way it turned out. Problem number 2, we have a beam and we want to find the reactions, and then I want to do a cut and find the moment halfway between the moments in the shear halfway between point B and point C. And so I'm going to start off by summing moments about point A, and I'm going to write the sum of moments about A, and I have a distributed load of 6 times the total distance of 2 feet. That's 6 times 2 is the total load, and its distance away from A would be that distance of 2 divided by 2. So 6 times 2 is the force, distance is 2 over 2. Then the other moment, let's see, RA causes no moment about point A. And I called moments that are counterclockwise positive. And so the moment due to F, which is the 500 times 2, is going to be a negative moment. My moment, which right here is 60, will be a positive 60 moment. Then my reaction, which I'm showing as positive right now, would cause a positive moment about point A, with that force acting through a distance of 5. And so I have one equation with RD unknown. That's one equation, one unknown. I solve that equation for RD and I get 185.6 pounds. Then I could just sum forces to get RA, and I'm going to do that in just a second. Instead, I'm going to sum moments about D first. Again, I'm going to say that counterclockwise is positive. And so summing moments about D, I've got the 60. I did in an odd order. I've got the 60 here. And I've got the 500 force acting through a distance of 3. Both of those cause positive moments. I've got RA causing a negative moment acting through a distance of 5. You can see that. Let's see. And I added in the 60 and the 2 and the 626. 6 times 2 is 12 is the force. Summing moments about D, that's a distance of 2 and 2. Let's see. 2 and 2 is 5.5. Let's. No. 2 and 2 is 4, and 1 is 5, and 1 is 6. It's acting through a distance of 6. 6 times 2 is the force. Moment arm is 6. This is one equation, one unknown in RA. So RA is equal to 326.4 pounds. And then to test that, I said let's do sum the forces and see if it is equal to 0. And so my forces would be a minus 6 times 2 from the distributed load in the downward direction, and a 326.4 upward at A, and a 500 downward, and a 185.6, and you add those numbers together and you do in fact get a 0. So I believe I've got the reactions right. Now the next part of the problem statement says calculate the internal shear and moment at the point halfway between B and C. And I didn't have to, but I'm going to do it from either side just in case any of you did it from either of the two sides. So I'm going to make my cut at that point, and I'm going to make my cut, and I'm going to look left. And I'm going to draw my shear force going in the upper direction. I'm going to draw my moment going in the counterclockwise direction. And then I'm going to sum forces in the vertical direction with up being positive. And I've got my distributed load 6 times 2 is 12 in the downward direction. I've got 326.4 upward direction. I've got 500 downward, and I've got that unknown internal shear force pointing in the upward direction. One equation, one unknown, solve for that shear force of a positive 185.6. Then I'm going to sum moments in the counterclockwise direction as positive. Sum of moments about point A, which is where that load is applied. I could go anywhere, but I chose point A. And I've got a 6 times 2 times 2 over 2 in the positive moment direction. I've got a 500 times 2 in the negative direction. I've got my shear force causing a positive moment, which is the shear force times 2.5, and then I've got my unknown moment causing a positive moment. I do know the shear force is a positive 185.6. I plug that in, then we have one equation, one unknown, and I solve for that moment of minus 524 pound-foot. Now, in going to the quote other side of the problem, instead of making my cut and looking left, I'm going to make my cut and look to the right. So I've made my cut here, and to the right I'm going to see that moment, which is a counterclockwise moment, and I'm going to see my reaction, and that's it. And to make these numbers work out, since this one was in the upper direction, the force acting on this side would be equal and opposite down, and my moment counterclockwise, so I'm going to make this moment clockwise. And I now solve for, and I know that because these are equal and opposite, they have to have the same sign value. So my sum of forces in the upward direction equals 0, and I've got my F shear pointing downward, that's negative, and I've got my reaction at point D, and that is positive. So my F shear is a positive 185.6. Now that positive sign means I got it right. It is in the downward direction. Sum of moments about point D, which is this end point, which will only involve the shear force and the applied moment, will be, and my unknown moment at the reaction is negative, and I said I would sum in the counterclockwise direction. So this one is in the opposite, so a negative of that unknown moment, and positive of the newly solved for shear force times its distance 2.5, and a positive of the 60. Plug in a shear force of positive 185.6 and solve for the unknown moment and get a net moment of negative 524 pound-foot. That's problem 2. Problem 3 is fairly busy. This is a gear on a shaft with a reaction from another gear, presumably a helical gear, providing these kinds of loads through the teeth of the gears, and our goal is going to be find the reactions at point A and at point B, and then draw some force, shear, and moment diagrams and some torque and axial load diagrams. And so I'm going to start off learning about stuff at B by summing moments about point A and saying that the sum of moments about point A are equal to 0. And the coordinate system that I have picked is X straight down the shaft, Y straight up, and Z coming out toward our left, and that does make it a right-hand coordinate system. Okay, so that's the coordinate system I've chosen. So summing moments about point A, I'm going to have a, now let's look at the conditions that we were set up with. We were told that this one is going to carry radial loads only, which are in the X, let's see, the Z and the Y directions. So these will carry radial loads only. Bearing B takes the thrust load. So this bearing carries all three loads, okay, and connected to the shaft at B is another device that's going to carry the torque. And so there is an unknown torque that's being resisted here, and so I'm going to label that as an unknown torque. Okay, so we have our, when I sum moments about point A, there is the moment due to the unknown torque, there is the moment due to the loads at C, and there are any moments due to the loads with the reactions at B. And let's see, yes, and that's it. And so we have that moment about, and that's an X direction moment only, plus the moment at C and R cross F, plus the moment at B and R cross F. Okay, and I, in writing this equation, left off the moment at X in the equation. It'll come back in more visible in the next one. And so my R cross F at C is an R that goes, since I'm at A, from A to C, and it goes 5 in the X direction, 3 in the Y direction, and 0 in the Z direction. 5, 3, 0. And the load applied there is a positive 400X, negative 450 in the Y, and negative 800 in the Z for the coordinate system that I've chosen. The loads, the moments at B would have a moment arm or a radius vector of 7 in the X, 0 in the Y, 0 in the Z, 7, 0, 0. Okay, multiplied by RBX, RBY, RBZ, and I'm presuming that all of these reactions point in the positive direction. Otherwise, I'd have to put some sign components on here. Plus that moment, which is just an X component only. Doing the cross products, since we have all numbers here, we get a numerical cross product here. You can check that. And we have 7, 0, 0 crossed with RBX, RBY, RBZ, which gives a 0 minus 7 times RBZ and a plus 7 times RBY. And then I still have that moment in the X term. And if I look at this, this is one vector equation that can be split into 3 scalar equations. If I take only the X terms, I'll get a minus 2400 plus 0 plus that moment in the X equals 0, which gives me that moment in the X, or that torque, is 2400. Then taking the middle row, I get 4000 minus 7 RBZ, nothing here, equals 0. And I get RBZ is equal to 571.4 pounds. And then my final equation, coming from the minus 3450 plus 7 RBY, minus 3450 plus 7 RBY equals 0, gives an RBY value of 492.8 pounds. So I've solved for the reactions at B. At least I've solved for some of the reactions at B. RBX, in fact, never came into the equation. It'll have to be found by other means. Step 2 is let's just sum forces. So sum of forces equals 0, so I have the reactions at A, and I don't have an X term here, I only have a Y and a Z term, and I'm going to set them as, show them in the positive direction. Okay, plus the applied loads from the gear, plus the loads that I've solved for at point B, including one of the loads that I wasn't able to solve for at B at this point. Sum of forces equal to 0. This first equation is going to go say 400 plus RBX equals 0, which gives me RBX equal minus 400. The second equation is RAY minus 450 plus 492.8 is going to give me an RAY of 42 pounds. The reaction at A in the Y direction, 42 pounds, 42.8. Then the third one, RAZ minus 800 plus 571.4 equals 0, gives me an RAZ of 228.6 pounds. And so I've found the axial thrust, the RBX, to be carried by the bearing at B, and I found the two components of the radial load. Okay, and then I want to check my reactions, and so I'm going to sum moments about point B and see what would happen for the loads at point A. So summing moments about B, I would still have that moment in the X direction. Then I would have the moments at A due to the loads at A. Let's see. No, these are the loads at C. Then we come to loads at A. The loads at C, I'm going to move at a minus 2 in the X, a positive 3 in the Y, 0 in the Z. Minus 2 in the X, positive 3 in the Y, 0 in the Z. That gives me the R. Cross with the loading of the 400 minus 450 and the minus 800. That gives me my moment of these loads about point B. Then the moments of the loads at point A about point B. The R vector is a minus 7 in the X, a 0 in the Y, 0 in the Z. And the reactions at A would be an RAX, which is equal to 0. Let's see. We'll just see what falls out of there, though, but that is 0. RAY treated as an unknown, RAZ treated as an unknown. Solving the two cross products, we get moment at X, the moment of C about B. This one does come out to be a 0 naturally, which lets us solve for the moment of X. And these other two are written in terms of RAZ and RAY. Solve the three equations, equation 1, equation 2, equation 3. Solve them for the unknowns, and we get exactly the same values that we had gotten back here for the unknowns. And so I would say that my reactions check. Now, to draw the diagrams requested, I'm going to draw, since X was my axis down the shaft, I'm going to draw an XY load diagram, shear diagram, moment about the Z direction. Since we're looking at the XY plane, we draw moments about the Z. And then we would look at the XZ direction, XZ loads, shear. Those shear loads cause moments about the Y direction. And then we would also look at the torsional load and the axial load. So the loading diagram is a minus 42.8 at point A. At point B, the load in the Y direction is a minus 450. The load in the Y direction at point C is a 49.2. So those would be our loads. Our shear diagram would say to go down 42.8, go over, go down an additional 450, bringing me to a 492.8. And then when I reach this side, go up a distance of 492.8, and we see that they close. So the statics is causing this diagram to close. Now, moments about Z, we're going to have to be careful. If we only looked at this diagram, we would miss something, because there is another moment about Z that we have to bring in. Our moment about Z will be the 42.8 back up here, multiplied by the distance that we travel to get the area under this section. And by the time we get to a distance of 5, we have reached a moment of minus 214. Now, looking at our picture, this 400-pound load does cause a moment about the Z direction, okay, and it is a positive moment, and so it's a moment of 400 pounds times a moment arm of 3, or 1,200 pounds. And so if we go up from minus 214, we go up 1,200 pounds in a step moment, we reach 986. And then the area under this section of 492.8 times the distance of 2 inches is 986. And so our moment, in fact, closes to 0 again. So this moment, which is the axial load times the radius of the gear of 1,200, very important. We can't leave that one out. Let's go ahead and look at the torsion load. Okay, so it's the magnitude of the torque in the shaft as a function of where it is on the x-axis. And initially, for the first 5 inches, we have no torque in the shaft. And then we have a torque of 800 pounds times 3 inches, so a 2,400 pound torque. And that continues, actually it continues on past the shaft until the coupling finally kicks in and takes it out. Alright, in the XZ direction, okay, looking back at the picture, the Z is positive, X direction, we're looking at this plane. And so in the XZ direction, we have loads of reaction of positive 228.6 in the Z, an applied load on the gear of minus 800, and a reaction at the other end of 571.4, positive in the Z. We saw for those earlier. So the shear forces would be the 228.6 going over to the 800, going over, and let's see, while we're at the 800, we're down at 571.4, and we have a final load of 571.4 to close the shear diagram. Our moment about the y-axis, since we're in the XZ plane, moments would be about the y-axis, and that would be the distance we travel away from the 228.6 load. Traveling 5 inches gets us to an 1143. 1,143. Excuse me. I'm still not feeling perfect. Okay, so it gets us there. Then the area under this curve, which is the 571 depth times 2, will bring us down back to 0 from the 1143. And the axial load acting on the shaft, this bearing carries no axial load. We have axial load coming in of 400 pounds, and it remains an axial load of 400 pounds through the shaft until we take it out at the bearing. So an axial load of 0, jumping up to an axial load of 400 pounds, jumping back to 0 at the bearing. And that is problem number 3, and that's the end of this movie.